All right, everyone. This is just a short-ish video to go through some of those questions that I handed out in class last week to do with specific and latent heat calculations. Hopefully this video will be helpful if you struggled with any of those questions to see how I go through it. I'm not going to go through every single question. This is just, I've picked out 5 questions from the sheet that I think give a pretty good idea, pretty good overview of what you'll need to do over the whole sheet. So if you've got any specific questions about something that I don't go through here, then be sure to let me know. Let's start with question 3. So we've got an immersion heater. It heats 2.5 liters of water, which it was initially at 15 degrees Celsius. It takes 3.5 minutes to bring the water to boil at 100 degrees Celsius. So we want to know at what rate in joules per second is the water gaining energy. So let's start with pulling out the important information. We've got 2.5 liters of water. That means the mass of water is 2.5 kilograms. We know the specific heat capacity of water is 4180. And we're told in this question that the water starts at 15 degrees and ends at 100 degrees. So that means the change in temperature of my water is 100 take 15, which gives me a delta T of 85 degrees Celsius. Now we have MC and delta T. So calculate my heat, Q, the heat gained by the water. So I'm going to do the next step now in solving these equations and write down the formula I'm going to use. Then substitute that in. So 2.5, it's missing there. 2.5 multiplied by 4180 times 85. And if we put that into our calculator, we get 888,250 joules. Okay, so that's kind of step 1 of this question, calculating the heat. For step 2, we are asked to work out the rate at which the water is gaining energy. So joules per second if it takes 3.5 minutes. Now, if we are asked to find joules per second, but the time given to us in minutes, then we first need to convert that time into seconds. So 3.5 minutes, there's 60 seconds in a minute. So if I do 3.5 times 60, I should get 210 seconds. And now if this here is my amount of energy in joules, and this here is the amount of time in seconds, then the joules per second is just going to be the joules divided by the number of seconds. And if I put that into my calculator, so I divide that by 200, let's start again, 888,250 divided by 210, I will get, no, I've done something wrong there, sorry everyone, I do 888,250 divided by 210, and I should get 4,200, and I'm going to round that up to 4,230 joules per second. I need to put that into 3 significant figures with scientific notation, so I'm going to call that 4.23 times 10 to the 3 joules per second. And also we know, we went through this in class briefly, that we can also call that joules per second. We have a term for that. It's called watts. So that's my final answer. Let's move on to question 7 from the sheet. How much heat energy is given out when 500 grams of steam at 100 degrees Celsius condenses and cools to 50 degrees Celsius? So here we're including a change of state. That means that before I start, I'm just going to get a quick idea of what's happening there by going back to the picture of this graph that we know so well by now. Okay, so we're starting with steam at 100 degrees Celsius. That's over there on this graph, steam at 100 degrees Celsius. And what's happening is that steam is first condensing. So it's all turning into water as it travels back along the graph in that direction. And then it's cooling down and finishing as water at about 50 degrees, which is about there. So it's condensing, and then the water's cooling down. So we're actually going to have two steps here. Let's write down all the important information. The mass of water is going to be 500 grams, so 0.5 kilograms. We know that the latent heat of fusion, which we're going to need for this bit of of what's going on. So the latent heat of fusion of water, we can check our formula sheet, and we get 3.34 by 10 to the 5. Hang on, sorry, that's a big mistake I've just made there. We need the latent heat of vaporization, of course, because we're involving a change from gas to a liquid. And the latent heat of vaporization is 2.26 by 10 to the 6. We know that once it turns into water, the specific heat capacity of that is going to be 4180, and the change in temperature, it's going from 100 down to 50, so that is a change in temperature of 50 degrees Celsius. Now we can do some equation writing. So that's our first step, writing down the important info. Now we need to write the equation we're going to use. So the total Q is going to equal, first we need to condense the steam. So that's ml. Then we need to cool that water down from 100 to 50. So that is mc delta T. Let's put in our values. Q equals 0.5 times 2.26 times 10 to the 6 plus 0.5 times 4180 times 50. We can put all of that into the calculator now, and let's see what we're going to get. So we can go 0.5 times 2260000 added to 0.5 times 4180 times 50. And we should get 1.23 times 10 to the 6. So that's how much heat has been given out. Let's move on to question 11 from the sheet. The question is, how much water at 32 degrees Celsius is needed to just melt 1.5 kilograms of ice at negative 10 degrees? Okay, so this is a question of thermal equilibrium, where the heat is being transferred from the warm water into the ice. So let's just have a quick look before we start writing any values down. Let's have a quick look at what's going on here. There's a key word in this question, which is just melt. So what we mean by just melt is that we don't want to warm the water up once it's been melted. We want just enough heat energy to melt it and no more than that. So if this is our graph, the warm water at 32 degrees, so that's about there. And then we're also starting with 1.5 kilos of ice at negative 10 degrees. So that's down there. And we're going to meet in the middle when the ice has just melted. So when it reaches thermal equilibrium, we want it to be right there. We don't want the water to warm up at all. We just want all the ice to melt. So the amount of heat that the warm water loses as it goes from 32 degrees down to 0 needs to be the same amount of heat that the ice gains as it warms up from negative 10 to 0 and then melts. Let's write down our values. So we've got the mass of water is what we don't know. The specific heat capacity of that water is 4180. And the change in temperature of that water is from 32 down to 0. So that's a change of 32. We also know that we have a mass of ice of 1.5 kilograms. We know the specific heat capacity of ice. We can look that up on our formula sheet if we don't know it. And the specific heat capacity of ice is 2.10 by 10 to the 3. And the change in temperature of that ice is from -10 up to 0, so that's a change of 10 degrees Celsius. And for this section of the graph, where it melts, we're going to need the latent heat of fusion. That is 3.34 times 10 to the 5. Okay. Now, the key thing here that you must write on your answer whenever you're answering these thermal equilibrium questions is the concept that the heat lost by the warm water is equal to the heat gained by the ice as it warms up and then melts. So let's see what each of these aspects, each of these components amounts to. The heat lost by the water, that's mc delta T as it goes from 32 down to 0. So that's going to be the water stuff. So that's m is what we don't know, the mass of water. We need to multiply that by the specific heat capacity, 4180, and the temperature change, 32. And that equals the total heat gained by the ice. So that's going to be mc delta T for the ice, which is 1.5 times 2,100 times 10. That's the heat gained as it heats up. And then we need the heat gained as it melts, and that's going to be 1.5 times the latent heat of fusion, which is, and I've run out of room here, so we'll just do 3.34 times 10 to the 5. Okay. The right-hand side of that equation, I've got all of my values. So let's calculate what that is. If I do 1.5 times 2,100, whoops, 1.5, let's start that again. 1.5 times 2,100 times 10. And then we're going to add that to 1.5 times the latent heat of fusion. Then we should get 532,500. So that means that the right-hand side equals 532,500. It means that I'm going to rearrange this equation to get m equals 532,500 divided by this stuff that was on the same side as m before. So divided by 4180 times 32. And when I calculate that, I get that my m is 3.98. So that gives me a mass of 3.98 kilograms. That is how much water is needed to melt 1.5 kilos of ice. Cool, moving on. Question 12. A 5 kilogram block of iron is heated to 800 degrees Celsius. It is placed in a tub containing 2 liters of water at 15 degrees Celsius. Assuming all the water is brought to the boil rapidly, calculate the mass of water which boils off. Okay, so let's just think about what's happening in this situation. I've got a tub, and I'll just draw a quick diagram of this. I've got a tub that's got 2 liters of water in it. And I have this 5 kilo block of iron, which I heat up really hot, and then I plunge into the water to cool it down. When it says that assuming all the water is brought to the boil rapidly, so that iron, when it drops into the water, it's going to heat that water up to 100 degrees Celsius, and then some of it is going to turn into a gas. So the task we've been given is to calculate the mass of water which boils off. So that means that not all the water is going to boil off, only some of it. But in order for some of it to boil off in this question, all of it is going to get up to 100 degrees. That's at least the assumption in this question, even if it's not always what happens in reality. Okay, so let's see how this is going to work. If the water's all getting up to 100 degrees, then it means the iron and the water, when they reach thermal equilibrium, are going to be at 100 degrees. Okay, now there's a couple of assumptions I'm making there that aren't necessarily true, because the question actually says that it's brought to the boil rapidly, but so again, in reality, this might not be what actually happens, but it's the assumption we're making in this question. So the iron and the water are both going to reach a thermal equilibrium temperature of 100 degrees. That means we can start writing down some values. The mass of iron is 5 kilograms. The specific heat capacity of iron, we're not told, I think we are told in the question on the sheet that I gave you. The specific heat capacity of iron that I'm pretty sure I gave you is 450. The change in temperature of the iron, it's going from 800 degrees, and then when it finishes, it's going to be at 100 degrees. So it's got a change in temperature of 700 degrees Celsius. Now, what's happening with the water? We have a mass of water of, well, it's 2 liters, so that's 2 kilograms of water. We know its specific heat capacity is 4180. Its change in temperature is from 15 up to 100, so that's 85 degrees. And then we also want to know what's happening, so that's all for the water. Then some of that water is going to turn into steam. So if we think about our graph again, what's happening is this. We're starting with water at 15 degrees Celsius. It's all getting heated up to 100 degrees Celsius. We've got enough heat energy to get it all to 100, and then we've got enough heat energy to get it part way along this bit here. So it's going to end somewhere in the middle there. We don't know exactly where. That's what we're trying to work out. So we're trying to work out how far along that path it's actually going to have enough energy to go. So how much heat energy does that iron actually have to give it? So I'm actually going to split this up. Instead of doing Q lost equals Q gained all together at the start, I'm going to first calculate the heat lost by the iron. The heat lost by the iron is equal to mc delta T, which is 5 times 450 times 700. And we can calculate that to be 5 times 450 times 700. 1.575 times 10 to the 6. Okay, so that's the heat lost by the iron as it cools from 800 degrees down to 100. Now, the key thing in thermal equilibrium questions is that Q lost equals Q gained. So that means that the heat gained by the water is equal to 1.575 times 10 to the 6. Now, the heat gained by the water is made up of two different things. We've got this stuff, which is the heat gained by the water as it warms up, and then we've got the heat gained, so that's I'll call that the heating water. And then we've also got the mass of water that turns into steam, which we don't know, and the latent heat of vaporization, which I should remember because we didn't do it that long ago, but it is 2.26 times 10 to the 6. And that is for the heat necessary to boil the water. Okay, so the Q gained by the water, 1.575 times 10 to the 6, that's equal to mc delta T, 2 times 4180 times 85, plus the mass that turns into steam times 2.26 times 10 to the 6. That means that we can take this stuff here and move it over to the other side of the equation by subtracting it. So 1.575 times 10 to the 6, we're going to take away 2 times 4180 times 85, and we're going to get 864,400. So we get that 864,400 is equal to 2.26 times 10 to the 6 times m. Therefore, m equals 864,400 divided by 2.26 times 10 to the 6. So divided by 2.26 times 10 to the 6 gives me 0.382 kilograms, or 382 grams of water is the amount that boils away. Okay, very last question that I'm going to go through is question 15 from the sheet. The question is, a block of an unknown alloy, mass of 6 kilograms at 25 degrees Celsius, is placed in an insulated copper calorimeter, mass 10 kilograms, containing 2 kilograms of water at 15 degrees Celsius. If the resulting temperature is 18 degrees Celsius, what is the specific heat capacity of the unknown alloy? Okay, so this is like a copper calorimeter situation, but the opposite to the one we did in class. So instead of putting ice into the calorimeter and using the water to heat it up, we're putting a metal into the calorimeter and using the water in it to cool it down. So let's write down our values. The unknown alloy, I'm just going to use A for that, for alloy. So the mass of the alloy is 6 kilograms. The specific heat capacity of the alloy is what we don't know. It's what we're trying to work out. Now, the change in temperature of that alloy, well, it starts at 25 degrees Celsius and it drops down to 18. So it's got a change in temperature of 7. Now, we've also got the calorimeter. So the mass of the calorimeter is 10 kilograms. Oh, that's a big calorimeter. The specific heat capacity of copper, I think you got it in the question, 385. And the change in temperature, well, remember the calorimeter starts at the same temperature as the water, so it's gone from 15 up to 18. So that's a change in temperature of 3 degrees Celsius. And then the last component is the water. So the mass of water is 2 kilograms. Specific heat capacity is 4180. And the water has also gone from 15 up to 18. So that's a change of 3 degrees Celsius. Okay, now we have our big principle of Q lost. The heat lost by the alloy is equal to the heat gained. In this case, it's the heat gained by both the water and the calorimeter. So the heat lost by the metal is equal to the mass, which is, so mc delta T, all for the alloy, is equal to mc delta T for the calorimeter plus mc delta T for the water. So let's put in our values. 6 times C, that's what we don't know, times 7 is equal to 10 times 385 times 3 plus 2 times 4180 times 3. That means we can rearrange this and we can say C is equal to 10 times 385 times 3 plus 2 times 4180 times 3 divided by 6 times 7. And let's calculate that. So the numerator there, I've got 10 times 385 times 3, and I'm going to add that to 2 times 4180 times 3. And then I'm going to divide that whole thing by 6 times 7. And I should get C of 872. So C equals 872, and always remember to put units on the end of your answer. So that's joules per kilogram per Kelvin. There we go, 5 questions. I hope that was useful. If you have any follow-up questions on any of those, something I did that you didn't understand, or if there's a different question from the sheet that you'd like me to go through, please let me know. You can let me know in class, or chuck me an email, or I guess write it in the comments. I'll see that too. And I'll see you all soon.